Fu, I got something on my hand. I'm kind of concerned about it. Not sure what it is. It might be a mole. Do you mind taking a look?
Sure.
Hey, I just met you, and this is crazy, but here's my number, so call me maybe.
That's right. Today we're talking about moles and gases. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu coming at ya. I'm your host Shu, and with me as always is Fu.
What up, nerds?
So Fu, in the last episode we talked about an ideal gas and used the ideal gas equation.
Yeah, and in this episode, we're going to kind of wrap up the unit and kind of finish off ideal gas equations with some more calculations involving moles. So let's get started. More ideal gas calculations, a lesson from the phases of matter unit. What? Let's talk about molar volume. Molar volume is the volume of 1 mole of a gas at a given temperature and pressure. It's implied that N equals 1 mole in the ideal gas equation, even though it's not stated specifically. So since it's just an assumed 1 mole, that 1 is not a measurement, so you wouldn't take that into account when doing significant figures in your calculation. All right, ladies and gents, we're gonna do an example here. Shu, are you ready?
I'm ready.
All right, what is the molar volume of an ideal gas at STP? We got a calculation here, and I got no numbers in this equation. You think you can handle it?
I don't know, that's what I'm worried about. There's
All
no
right.
numbers.
Let's try. All right, so we've been talking about the ideal gas law. That's the equation we're using.
Okay.
So with our formula, let's start there.
All right, so I've got PV equals nRT.
All right, so we gotta pull some numbers out of somewhere here, and there is a little trick here that you should be familiar with by now in the unit, and that is those 3 magical letters of STP.
Okay, I'm remembering a little bit now.
So what does that stand for?
All right, so standard temperature and pressure.
Okay,
So I actually do have my temperature and pressure given to me, even though no numbers are written.
good.
All right, so I think that means I can use 1 atmosphere.
Latum over molk.
Right, I
It's
need
gotta be in atmospheres.
Exactly, so, and that's from table A, right?
Yep,
So standard pressure is 1 atm. I'm putting that in for pressure.
good. The next unit is volume, but according to the question, what should we know about volume here?
It says what is the molar volume, so this is actually what we're trying to find.
Good, so that's our variable we're gonna solve for volume. Now this says molar volume, so like we just discussed, N being moles, we're gonna have an assumed 1 here, so just 1 mole.
Okay, so if they just say molar volume, they're specifically talking about the volume of 1 mole.
Of 1 mole.
So I just put in 1 mole for N, that's it.
Yep.
Okay.
R should be pretty easy too.
All right, that's a constant, 0.08206. That's the atom over mole. Put that down below for space. And then temperature. Oh, standard temperature again. Gotta be
That's right.
Kelvin. So 273 Kelvin.
Okay, so we actually got numbers from a question that had no numbers in it.
Awesome.
All
So
right.
just have to multiply everything on the right. Well, I'm just dividing by 1 at the end. And I mean, I guess there aren't really any sig figs, no measurements. I guess I'll just take it out to 3. So volume is 22.4 liters. That is the volume of 1 mole of an ideal gas at STP.
Very good.
Now that we just solved for the molar volume of a gas at STP, this can now be used as a conversion factor, as long as we know we are at STP, definitely. So our conversion factors are as follows. We can either say in 1 mole of gas, there's 22.4 liters of gas, or we can say in 22.4 liters of gas, there's 1 mole of gas. Okay, we're gonna do an example where we use this new conversion factor. You ready, Fu?
I am.
All right, how many molecules of gas are found in 1.20 liters of H2 at STP? Now, we've got the volume given there. It says at STP. We could very easily use PV equals nRT. But we're gonna actually try doing this using only dimensional analysis. We're gonna kind of show you a
Okay.
different way of doing things. All right, so what are we given in this problem?
We are given the 1.20 liters of
All right.
H2 gas.
Very good, let's start with that. We'll write that down. That's what we're gonna be converting. And what are we trying to find?
It says how many molecules? So molecules.
All right, good. So we're going to convert liters first. We actually don't know a way to convert liters directly to molecules, but we just learned a new conversion factor where we can convert liters to what unit?
To moles.
Very good. All right. So let's multiply by a conversion factor. What unit will go in the denominator?
The liters of H2.
Good. And how about in the numerator?
Moles.
Good.
H2.
Good. So let's put in our numbers. What numbers go there?
So it's molar volume, so it's per 1 mole, right? So 1 mole of H2 is 22.4 liters of H2.
Good, and just to reiterate, it doesn't matter which gas it is, it's 22.4 liters in 1 mole, as long as they specify that we are at STP. If we're not at STP,
Okay.
we don't know that it's 22.4 liters in 1 mole.
And then I'd have to use those other equations.
Then you'd have to use
Okay.
Putnert again. Good. All right, we've got one more step. We're going to convert moles to molecules.
All right, so moles, H2 down there, and molecules.
Good, let's fill in our numbers here.
Let's see, 1 mole is Avogadro's number of 6.02 times 10 to the 23rd molecules.
Very good. We're going to do some multiplication and division here.
Okay, so when I multiply 1.20 by 6.02 times 10 to the 23rd, divide it by 22.4, I get, let's see, 3 sig figs because of the 1.20.
Good.
So 3.23 times 10 to the 22nd. And that would be, let's see, liters cancel out. Moles cancel out. I'm left with molecules, so my unit is molecules H2.
Well done. You try number 1. How many liters contain 2.36 times 10 to the 24 molecules of O2 at STP? Please use dimensional analysis, proper units, and sig figs.
Let's talk about gas density. So gases occupy larger volumes than solids and liquids. As a result, their densities are expressed in grams per liter, as opposed to grams per milliliter or grams per cubic centimeter. All right, we're gonna do an example here of gas density. Shu, are you ready?
Yes, I am.
All right, if there is 1.00 moles of Ne, what is its density in grams per liter at STP? All right, so we're doing density, so our formula should be?
Well, this is off of table T. Density equals mass over volume.
Okay, so what is this question giving us?
Let's see. They only give us 1 mole.
That's not in our equation at all, right?
No, and I know I'm
Okay.
trying to solve for density, but I'm gonna need the mass and the volume.
Okay, so let's break this down a bit. Let's hold off on mass for a second. We
Okay.
have discussed volume of a gas, right? So we have 1 mole of a gas, and is it at STP?
Oh, yeah. Look.
So if we have 1 mole of a gas at STP, we can use molar volume.
Right. Okay, that's a set number as long as we're at STP.
Yep.
So it's 22.4 liters that are in 1 mole.
That is
right?
correct. So we've got the volume.
All right, so I can just put that in. And I wanted the units in grams per liter, so I'm good with it being 22.4 liters.
Okay, so we're only missing what now?
The mass, well, I'm assuming it has something to do with the 1 mole again, right?
Okay, so we have 1 mole of neon. So what is that in grams?
So the amount of mass in 1 mole is the molar mass, and that I can just get from the periodic table looking at neon, right?
That's correct, yeah.
Okay, so for neon is on the periodic table 20.18 grams. That would be the mass of 1 mole.
That's correct.
All right, so that's not so bad. I just have to divide the mass by the volume, and I guess I'll use 3 sig figs from the 1.00 mole, and I get 0.901 to 3 sig figs off my calculator. Units are grams per liter. Is that a reasonable number there?
That looks pretty good.
All right, good. All right, we're going to return to Avogadro. This is Avogadro's hypothesis. At STP, equal volumes of a gas have an equal number of molecules, which also means an equal number of moles. Who cares? Well, even 2 equal volume containers of 2 completely different gases with different molar masses will still contain the same number of molecules. Putting it all together, something you can find off of table T, 22.4 liters equals 1 mole of gas equals 6.02 times 10 to the 23rd molecules.
So looking at the diagram below, we have 3 different gases. We have argon, we have oxygen, we have nitrogen. Now these are 3 different gases. They have 3 different masses, but because they're all the same volume and pressure and temperature, it's all the same quantity. They're same moles. They're all 1 mole.
All right, we're gonna do an example that makes use of Avogadro's hypothesis. You ready, Fu?
Let's do it.
All right. Container A contains 2.00 moles of AR. Container B contains 2.00 moles of KR. Both containers are at STP. Fill in the chart. All right, so let's start with temperature and pressure. So Fu, what clues are there in the question that would tell us the temperature and pressure?
Well, I know it by now. STP is standard temperature and pressure. So STP right there means that both temperature and pressure of both of these gases are standard.
All right, good. So let's reveal the contents of those cells.
Both 273 Kelvin, and they're both at 1 atmosphere.
All right, very good. So those 2 variables are the same for both containers. Let's continue on with volume. We actually have 2 moles present for both of these gases. So what are you thinking here?
Well, I'm thinking that I remember 1 mole of a gas at STP, which we just said we're at, is 22.4 liters. But in this case, the question says I've got 2 moles, so I'm just gonna multiply that times 2.
Sounds good.
Okay, so
Reveal.
do that, 44.8.
Yeah, 44.8 liters. All right, so these first 3 variables completely the same. Let's look at the mass. Again, we know the moles. How can we find the mass?
All right, well, mass is also based on the type of substance you have 2 here. So, and I do have 2 different gases,
Right.
and they're gonna have different masses. I've got argon and I've got krypton, but they're both 2 moles, so I can convert moles to grams easily just by multiplying times the formula mass. So I'm just gonna multiply times their atomic masses times 2.
Sounds good. Reveal. All right, good. So for both, we took 2 moles, we multiplied by each one's respective molar mass, and we got 2 different values here, right?
Okay.
All right, and finally we have density. Looks like now we filled in our chart with mass and volume, so mathematically, what should we do?
Just have to take mass and divide it by volume.
All right, good. So what do we get? Reveal. All right, so we've got 2 different densities as well for these 2 gases.
Even though it's the same temperature, pressure, and volume.
Very good. You try number 2. Container A contains 11.2 liters of argon. Container B contains 11.2 liters of krypton. Both containers are at STP. Fill in the chart. Now this is going to be pretty similar to the chart we filled in previously. There's a few things that are a little bit different. Think about what might be significant about the volume 11.2. Anywhere that you need to show work, show it right in the cell. Well, that's going to do it for today's episode on more ideal gas calculations.
Later, nerds!
Promotional consideration by
Meezy's Custom Car! You want your car to look like 2 bicycles going down the road? Give us a call!
But we never off or we zone till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie like my homies, boys to men. It's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.